Let's take a look at another example. Let's see if we can find the inverse of the Laplace transform of s squared plus 6s plus 9 divided by s minus 1 times s minus 2 times s plus 4. One of the things that we're going to need to do is we're going to need to employ a technique that you might have seen in the college algebra class, or certainly at least you probably saw in calculus 2, which is going to be the idea of using partial fractions. In order to apply our inverse Laplace rules, what we need to do is we need to decompose this fraction. So we want to write s squared plus 6x plus 9, which right now is over the product s minus 1 times s minus 2 times s plus 4. We would like to split apart the denominator into its distinct linear factors. So we should be able to write this as a over s minus 1 plus b over s minus 2 plus c over s plus 4. And I'm not going to create a separate review on this. If you feel like you're rusty on partial fractions, I can link to some other videos that might help to give a refresher. But you have to kind of remember how things kind of change. If you have a factor that's repeated, or potentially if you have If you have a repeated factor, or if you have irreducible quadratics, is the other case for your factors in the denominator. But for the one we have in example 3, we're going to try to decompose it. What we can now do is we're going to clear fractions by multiplying both sides of the equation by s minus 1 times s minus 2 times s plus 4. And its poor form, I should really show this on both sides, but just because I don't have a lot of room to work with, you're essentially multiplying both sides by this. What that will give us now is going to be the following. It'll cancel on the left-hand side, so you would get an s squared plus 6s plus 9 is equal to, and now you would take turns distributing it into each of the terms here. When you distribute it to the first term, the s minus 1s would cancel, and that's going to leave us with an a times s minus 2 times s plus 4. Plus, when we distribute it to this term, the s minus 2's cancel, and so we get s minus 1 times s plus 4. And we distribute it into the last term, the s plus 4's cancel, and we get c times s minus 1 times s minus 2. From here, there's two different approaches you can get in order to solve this. We have 1, 2, 3 unknowns, a, b, and c, and to solve for them, one of the things you could do, and this is a really good method, especially when you get the irreducible quadratic factors, is to expand the left-hand side, combine like terms, and then you can kind of use the method of equating coefficients. Expand the right-hand side, combine your like terms, you'll be able to write it as some polynomial in s, it'll actually be a quadratic in s, and then you would just kind of equate the coefficients. That is a fantastic method to use. Again, typically when you have irreducible quadratic factors, as well as non-repeated linear factors. If you have something like this where none of our factors are repeated, then we could actually solve for s, for a, b, and c by making convenient choices of s. For example, we see that the term that would make this equal to 0, if I let s be equal to 1, then this term is going to be 0, and this term is going to be 0, and we would be able to directly solve for a. So let's let s be equal to 1. If I plug that in to this equation, we get 1 squared plus 6 times 1 plus 9 is going to be equal to a times 1 minus 2 times 1 plus 4 plus, plugging it into here is going to make this coefficient 0, so this whole term is going to be 0, and plugging s equals to 1 into here is going to make this factor 0, so that whole thing is going to be 0 as well. So what we end up with is that we have 1 plus 6 plus 9, which is 16, is going to be equal to, this is negative 1 times 5 is going to be negative 5a. So we get that a is going to be equal to negative 16 fifths. We can now do the same thing to solve for b. Notice the factor that was under b was s minus 2. If we let s be equal to 2 in this expression here, then this first term will cancel, this last term will cancel, and we'll be able to solve for the coefficient b. We get 2 squared plus 6 times 2 plus 9. It's going to be equal to, again, that's going to be 0, plus b times 2 minus 1 times 2 plus 6 plus 0. 2 squared is 4. 6 times 2 is 12. 4 plus 12 is 16, and then 16 plus 9 is 25. So we get 25 is going to be equal to, this is going to be 1 times 8, which is 8. So we get 25 equals to 8b, and therefore b equals 25 eighths. We can now go ahead and solve for, hold on one second here. This was s plus 4 as a factor, so this should have been plus 4. It's one step ahead of myself. So this should have been 6b equals to 25, and so b is going to be 25 sixths. Try to do 2 steps at once. And now if we want to solve for c, the thing that would make the factor under c equal to 0 would be negative 4. So let's go ahead and let s be equal to negative 4. When we plug that in, this factor would cancel, this factor would cancel, and we can solve for c. We get negative 4 squared plus 6 times negative 4 plus 9. It's going to be equal to, this will be 0. This one will also be 0. And then we're going to get plus c times negative 4 minus 1 times negative 4 minus 2. That's going to be 16 minus 24 plus 9. That's negative 8 plus 9, which is 1. Put it here. Equals, and then on this side, we have a negative 5 times a negative 6. Should give us a positive 30. And then divide both sides by 30 until we get that c equals 1/30. So that's how partial fractions works. Again, there's more than one way to do this, but oftentimes, especially if you have the linear factors that are non-repeated, this choosing convenient choices of s tends to work out very, very well. So what do we now know? We are able to rewrite our function we're trying to find the inverse Laplace of. So the inverse Laplace of this s squared plus 6s plus 9 divided by s minus 1, s minus 2, and s plus 4 is going to be the inverse Laplace of it, but in this expression here. So this is going to be the inverse Laplace of a, we said was negative 16 fifths over s minus 1, plus b was 25 sixths over s minus 2, plus c, which is 1 over 30 s plus 4. We can now use the linearity of the inverse Laplace operator. This is equivalent to negative 16 fifths times the inverse Laplace of 1 divided by s minus 1 plus 25 over 6 the inverse Laplace of 1 over s minus 2 plus 1 over 30 the inverse Laplace of 1 over s plus 4. And now what we can do is we can invoke our basic inverse Laplace rule. If you recall that the inverse Laplace operator of 1 divided by s minus a, this is equal to e to the at. Therefore, we get negative 16 fifths. And now here, in this case, s is playing the role of 1. So it's going to be e to the 1 times t, which is e to the t, plus 25 sixths. This is going to be e to the 2t plus 1 over 30. Be careful with this last one. Because you see a plus sign here, essentially that's saying that a is equal to negative 4. Because you can think of it as s minus a minus 4. So it's going to be e to the negative 4t for the last one. Okay. So a very common technique. I hope this particular example, I think you might find to be very helpful. But in general, whenever you do the inverse Laplace transform of a rational function of s, what you would want to do is these steps. Factor the denominator completely. So luckily for us, that step was already done. It was presented as s minus 1 times s minus 2 times s plus 4. So it was already factored. The next thing you'd want to do is write out what the partial fraction decomposition would look like. Write out an equation that represents a, b, and c, usually by clearing denominators. And then, again, if you remember how to do partial fractions, there's a couple different approaches. You can either choose convenient values for the variable s. If you, in general, have n unknowns, a, b, and c, we had 3 unknowns, you would need to make 3 choices of s. However, if you have repeated factors or irreducible quadratic factors, then the choices of s won't necessarily immediately always provide values for a, b, and c, in which case you might want to do the method of equating coefficients to work out the partial fraction decomposition.